All right, let's jump into electroplating. Now I'm trying to do a couple things here. We'll see if it works, see if I can even show you the demonstration that I would have shown you in class. So in your notes, we're on this part of the page here. And right away you'll notice in this cell right here that there's a difference between the voltaic stuff that we've been doing and the electrolytic stuff. There's only one beaker. Rather than having two separate cells that each contain half of the reaction, this is all just taking place in one beaker. So that's the first thing you'll notice about electrolytic cells. The second is up higher at the top there where this is a battery. So remember that these are non-spontaneous reactions. They require voltage to force these reactions to take place. So if you ever see a reaction that has a battery or power source or anything like that, dead giveaway, that's an electrolytic cell. Okay. The other thing is you'll notice on this diagram that it lists, or that it shows here on the side, this right here, it shows the electron flow. So in this case, rather than determining our anode and cathode based on the strongest oxidizing agent and the strongest reducing agent, we base it on where the electrons are flowing. So since the battery is forcing electrons to travel this direction, I know that energy always flows from the anode to the cathode. So just by that arrow, I can already label on my diagram the anode and the cathode. So that's something to remember as well. All right, let's take a look at an example here though. Let's say you've got a beaker, and in that beaker you've put copper sulfate. So I have copper, 2 positive ions, and SO4, 2 negative ions. I'm going to put in here, I'm just going to draw it like this, a power source. Remember that the electrons always come out of the battery on the negative terminal. So when we draw like this, let's say, I don't know, let's say we've got a key, something like that over here that we're going to plate. That's hooked up to the negative terminal, and on the other side, for this example, I'm just going to draw a strip of carbon solid. Remember that carbon is an inert electrode, so it's not involved in this reaction at all. Okay? Now, in terms of what I have here, if I were to list this all out to try to figure out the reaction, I would have to list out, I have copper 2 positive, I have SO4 2 negative, I have water, and we don't list the carbon because it's inert, and we don't in this case even have to mention the key or worry about what metal the key is made out of because the electrons are being forced into it. So let's label our electron flow. So that key won't have a chance to react because we're forcing electrons into it. It won't have a chance to react itself, so we can kind of ignore it. So that's really all I have. I've got copper 2, I've got sulfate, and I've got water. So if we look at our data booklet, remember that water is on this page twice. So on the RA side over here, it's at positive 1.23, if you can see that. And water as an OA is right here. Okay. Pardon me. So it's not a very strong oxidizing agent. It's not a very strong reducing agent. But the only other thing we have here is right up here, copper. We have copper 2. So copper 2 is my SOA. And since I don't have anything else except for the sulfate, actually let me point this out. Sulfate is kind of like nitrate, that if you take a look at your table, it only shows up on the table with something else. And in almost every case, at least part of that something else is acid. So if you don't have sulfate but you don't have acid, almost guaranteed the sulfate's going to be a spectator. So in this case, that's my SRA, is just the water, since the sulfate is a spectator. So we're going to write our two half reactions. Let's go back to this. So copper 2 plus 2 electrons becomes copper solid. And for the water half reaction, remember this is water as an Ra, I have 2H2O is turning into oxygen gas plus 4 H positives and 4 electrons. So if we were to just try and balance, let me get out of the way there. If we were to try and balance this equation, in fact maybe I'll hide me here for a second. We would have to times this reaction by 2, cancel out the electrons, and we would end up with a net reaction of 2 copper 2 positive plus 2 water will become 2 copper solid plus O2 and 4H positives. Okay? If we wanted to figure out the voltage that we would need, remember that the coppers are OA, so we're going to leave that one alone. So that's a positive 0.34 volts.
And someone was trying to get hold of Louisa shouting mother, or Louisa, could you please call 0?
Sorry about that. And if you look at the water, it's as our Ra, it's way up high, 1.23, so now that becomes a negative 1.23 volts. So when I combine these, you're going to see that we've got a negative voltage, which, let me grab my calculator quick because I don't feel like doing math in my head, which is negative 0.89 volts. So sorry, I'm a little cramped there. So that means in order to make this reaction work, we would have to pump in out of our power source at least 0.89 volts to make this work. But if we look at our half reaction to see what's actually taking place here, I have copper 2 ions becoming copper solid, and since that's my oxidizing agent, my reduction half reaction, I know that's happening at the cathode. So in this case, the key is the cathode, which means that the copper ions are moving towards the key, the cathode, to pick up those electrons and become solid. So on the surface of the key, we start plating solid copper. If we look at the other half reaction, we have water turning into oxygen and hydrogen ions. So from the carbon, the solid carbon anode, we would start to see bubbles forming, and those bubbles would be oxygen gas. And this cell could run as long as you wanted, as long as you didn't run out of copper, then you would be fine. This is where we kept adding copper, 2 ions. You could keep plating more and more copper onto the key. This is how they would do, for example, copper plating of silverware or chrome plating a bumper or things like that. It would all be done through a process very similar to this. Okay? Now, let me see if I can set this up so that I can show you what this would actually look like. It'll let me. Okay, let's see if this works. So this is our power source. So I've got this plugged into the wall. So that's going to provide our power. We've got our negative terminal here in the black, and we've got our positive terminal here on the red. We've got some electrodes here that allow our wires to allow us to hook things up. And what we're going to try to copper plate is this quarter right here. Okay. Now this solution, I'll let you take a look at that, is a copper sulfate solution. And we've added to it, so exactly like our reaction, a copper sulfate solution, but we've added to it some acid. And that acid just provides some more ions to allow this to work a little bit better. All right. Now we're going to hook up our electrodes. Maybe. Come on. There we go. And we've got a solid carbon rod here that we can use as the cathode. And we'll hook the quarter up as the cathode, or the anode, I mean. Okay, now remember from our calculations we said we would need a minimum of 0.89 volts. So we'll start here at the lowest setting, which is 1.5 volts. And we'll see what we can make happen here. Now, let me see if I can move the camera here. See if you can see what's going on. So you'll see there, we've already got a small amount of copper plating onto the quarter. Sorry, it's out of focus. I don't think my webcam can focus quite that close. But there you can kind of see a real thin layer of copper forming on there. Now at this small voltage, we don't really see the oxygen gas being produced yet. The carbon is kind of porous, and so the gas bubbles are probably forming inside, and they're not showing up real well right now. However, if we wanted to make this a little more dramatic, we would just up the voltage. And now you can see those bubbles being produced. Now there's also bubbles being produced here on the quarter. That's just because I'm cranking way too many volts into this all at once, and the system is reacting more than it wants to. Okay? Okay, so now you can see on that quarter that there's a really small amount, because we didn't run it for very long, there's a very small amount of copper on there. And that's on there pretty solid. Right, I can't rub that off. It's not really polished or anything, but it's on there. It's on there pretty good. Okay? So that's how electroplating works. Let me move this stuff out of the way. Be right back. All right, let's jump back into here though, because I want to show you one more thing. In this half reaction, we used copper and we used the carbon, which means that we ended up with an actual voltage right here, the negative 0.89 volts. There may be times though where, for example, if you look up at this diagram that I gave you in the notes, you'll notice that the anode in this case, well, I think I said key was the anode earlier. My bad. The key is the cathode. That in this case the anode is silver. So in this case, silver is your strongest reducing agent, and silver ions are your strongest oxidizing agent. But if you were to write that out, it means that the whole reaction cancels itself out and that you get a zero voltage. That still means it's electrolytic. It's still a non-spontaneous reaction. But just be aware that the advantage of that is, in our example over here, when the copper was being used up from the solution, we had to keep adding copper. In this case, rather than adding copper into the solution, they've added the silver strip. So as the silver reacts, you get more Ag positive, and then the Ag positive goes on the spoon. And then you get more Ag positive, and then the Ag positive goes on the spoon. So they're just putting in a silver electrode, and that process is moving the silver atoms from the electrode into the solution in aqueous form and then onto the object that you're trying to plate. So the trick here is always remember that the Electrons come out of the negative terminal if they show you a negative. If they show you electron flow, that tells you anode and cathode, right? That's very important. And that whatever you're plating, whatever you want to put the stuff on, like our quarter, is always the cathode. We want to force the electrons into this so those positive ions are attracted and want to pick up those electrons at the cathode. Okay? All right, if you have any questions, let me know, but hopefully that makes sense.